Okay, class, welcome back. So now we're kind of at the conclusion of everything we've worked towards. This is the last chapter of your book, actually. And we're going to kind of use everything we've learned to talk about turbo. Okay, so these are the pumps, right? So you all have a good idea of, getting this sort of H pump, converting that to a power requirement. Okay, so you've done that in your projects, and you kind of see it's a fundamental thing that engineers are going to do a lot. But this section is about, well, how do I actually select this pump? And that's a big, big part, sort of that second phase of what you do in something like your project. You get an estimate of what that pump is, and then you need to get into what pumps can I actually buy to achieve the best possible case. You usually can't just get that number and then achieve it. So before we go along, I think you should all appreciate sort of how these classes go always, is you have some theory, right? You turn that into some equations, and then what have we done every single time? Every single time, right, we use that to calculate energy. So it's the exact same process we'll do with these turbo machines. We're just doing it in the reverse of looking at what a pump would look like to get then the energy that, based on all these parameters, what kind of energy can I get? So, right, it's the idea of figuring out the actual pump. Right, that's what we're trying to get at. So what do pumps do, or turbo machinery is a better name for them, right? There are these classic diagrams here where they add, right? They could add head to a water system like the one you've done, right? In these drag situations of planes, if you watch those ones, right? They can do this. They can maintain or in the case of a windmill, right? They can harvest. So that's what windmills will do. They're turbo machineries, but they're compressors. So what they're doing is they're taking the energy out of the flow field. So I say maintain for external because that's what you're usually fighting about. So, these are sort of the three topics we're going to go over for turbo machineries, and or just really how far stretching the process, right? How far stretching these equations are that you can use, that they can actually describe all three of these scenarios. Whether it's an external flow for a plane, whether it's your classic like pipe flow, your project is in this one, but still you hopefully you'll get a sense of just how far-reaching this section is. And even for windmills, the exact same physical reasoning processes go in for this. That's for all of them. These are compressors. So we also have we call them turbo machineries because it's just right because we call them turbo machines. Okay, so it's a pretty large term, right? These are what we're going to study for this section, and they range from here, just a bunch of examples I think I wrote down, right? We have like a window fan as an example. We have like propellers, axial flow water pumps. You'll see what axial means later, right? A steam turbine. Also a turbo machinery, right? Compressors. Anything else I have? Oh, a turbocharger. And the list goes on and on and on for just all the different types of machines that really are a turbo machine. So, what did I have for just this introduction? Okay, so that's maybe, I guess, the motivation of just how many things this section talks about, so maybe why you should pay attention. Oh, no, I got 4 minutes. Okay, we'll just keep going. Okay, so again, right, the goal of any sort of section we do in this class is to try to get some sort of energy value from it at the end of at the very end when we have derivation equations and things like that. So one thing I want you to think about for any of these types of pumps is if you have maybe it's like an axial flow problem like this, where I've send water in through this way, and it's actually going to come out this way, right? And you can just know from these designs of what you have is you have these like impellers that come through here. You might not be able to see this. This section involves a lot of drawing, so I don't think it's that good on my chalkboard, but I tried my best on my notes to make the pictures look nice at least. So for this pump, right, this is the process of, right, we're going to add energy into the system to rotate that propeller, or impeller in this case. So, right, it has some angular velocity of what that impeller is rotating at, and then it just has all these dimensions, you could say, to it as well. Like there's tons of them. Like there's a diameter for this pump right here. Let's say there's a smaller diameter of the inlet and the outlet. You can measure these things with any sort of tool you want. So that's one type. Okay, the other type is just your simple like box fan, right? Right? You put these things in your windows a lot too, right? So for here, still what you have is some impeller design right here, right? And you still have some, right, radial velocity like there, and then what happens is here, you have kind of a small flow rate at in the back of your fan, but then out right in where you want the air to go, it's actually moving really fast. So just put your hand behind a fan, you can actually realize this, and this is one of these axial fan flows that we can discuss too. But again, right, think of the exact same scenario, right? We have this parameter of axial velocity, we have a diameter, you can have, again, right, you take this system, what do? You add energy to rotate that impeller. That's what you plug it into the wall for. So, and then lastly, we have that example of what? You have these windmills, right? It's very eco. So maybe this kind of looks like a German like windmill house, but they're easier to draw, right? So for something like this, you have a flow field moving, the wind. Again, though, right, you see that the wind is then causing an axial velocity. We still have a diameter of the propeller, and the only difference here is now in this case, there's a flow field moving into the windmill, and what's going to happen here, that's what we're doing. So right, in this case now, the energy is going to be harvested from the flow field. So it's just a reverse of an arrow for this case, but the same analysis can apply for both cases. But I wanted you to see how really, if you just looked at all the different cases, you would see some axial velocity and look at some diameter. So these are some of the parameters that we can tell are just going to be important, right, regardless of the incredibly complex physics that would happen from looking at the interactions of the actual blade, etc. Right? In a bulk sense, I know I should look at the diameter, and I know I should probably consider this velocity as well. And I probably should just consider lots and lots of, right, dimensional variables involved in the propellers, like the length of them, right? Maybe this has its own diameter. Clearly, those are going to come into play if we're trying to figure out what this energy term is going to be. And that's going to be this next section where we go over, like, how do you just estimate some things?